Centripetal force. For an object to experience uniform circular motion, it must experience a centripetal acceleration towards the center of its circular path. That centripetal acceleration is perpendicular to its velocity and has a magnitude of v squared over r. What does that tell us about the force acting on the moving object? The net force on an object is in the direction of its acceleration and has a magnitude given by force equals ma from Isaac Newton. So for an object in uniform circular motion, there must be a net force acting on it directed to the center of the circle and perpendicular to its velocity. This is called the centripetal, that is, center-seeking force. And here we are. Same direction as the acceleration. Newton's second law again. Sum of the forces is ma, or the acceleration is the sum of the forces over m. If an object is in circular motion, that is uniform circular motion, it has an acceleration directed towards the center of the circle with a magnitude of v squared over r. Combine those equations to learn about the object, its motion, and the forces acting on the object. So the sum of the forces is ma, that equals mv squared over r for uniform circular motion. This equation does not describe the source of the centripetal force, or even that there is just one force acting on the object. It just says that the sum of all forces acting on an object traveling in uniform circular motion must have the above magnitude and be directed towards the center of the circular path. We will study cases where that net force is provided by gravity, tension, friction, etc. Any type of force could provide the needed centripetal force to keep an object moving in uniform circular motion. To understand why the force must be inward, one could think about a ball on a string. The ball has to be constantly pulled inwards towards the hand holding the string, otherwise it would fly off tangent to the circular motion. So here's the force on the hand exerted by the string, and here's the force on the ball exerted by the string. Imagine a bowling ball rolling across the floor. Here's your bowling ball, and you have been given a rubber mallet. How would you have to hit the ball to make it move in a circle? For the answer, click below for a video demonstration. You might have heard previously about centrifugal or centrifugal center-fleeing forces. However, in this course, we will only be dealing with centripetal, that is, center-seeking forces. The natural tendency of an object is to move in a straight line. To move in a circle, this tendency must be overcome with the centripetal force. If the centripetal force vanishes, the object flies off in a straight path. In more advanced college-level physics courses, you might learn more about centrifugal forces. So here we have a rotating ball here. The string gets cut. It will go off in the same motion that it had, which was tangent to the circle. It does not keep curving, okay? This is what happens. A centrifuge works by spinning very fast, which requires a very large centripetal force. The particle at point A has a natural tendency to go straight. It wants to follow a straight line. However, the walls of the centrifuge push the particles towards the center of the circle, so this specific particle winds up over here at point B. A 12-kilogram object has a velocity of 8 meters per second and is moving in a circle of radius 16 meters. What is the net force acting on the object? What is the direction of the net force? We write our givens, and then we use the equation. Sum of the forces is mv squared over r. We put in the mass, the velocity, and ensure that you square it, divided by the radius, and we get 48 newtons. The direction of the net force is towards the center of the circle. A 6-kilogram object is experiencing a net force of 12.5 newtons while traveling in a circle of radius 5.2 meters. What is its velocity? We're assuming a centripetal force here because they're asking for one velocity. So here's our equation. Sum of the forces is mv squared over r. We have to solve that for v. Multiply both sides by r, then divide both sides by m, and then switch it around and take the square root of both sides. So we get the velocity is the force times the radius over the mass. So here's our equation. We just move it there. Here's our force. Here's the radius. Here's the mass. Make sure you remember to take the square root. And the velocity is 3.3 meters per second. The first artificial satellite to orbit Earth, Sputnik, had a mass of 84 kilograms and orbited Earth every 5,900 seconds at a distance from Earth's center of 6.4 times 10 to the 6 meters. What was the magnitude of the gravitational force acting on Sputnik? We have our givens, and this is an example of a gravitational force acting as the centripetal force. So we have our equation here for force, and we're looking to find what that force is equal to. Now we're not given the velocity. However, we can use this equation where the velocity is 2 pi r over the period of the rotation. So we square that. Why? Because v is squared. We get this over here. And then we do some simplification, and we get the force is 4m pi squared r over t squared. We put it over here on the right side, and we put in all our numbers. We have 4, we have the mass, we have pi squared, we have how far it is from the center of the Earth, and then we have the period in seconds. Calculate all the numbers out, and we get a gravitational force of 610 newtons.